Hello. I am in a linear algebra class right now. I'm finishing it up in a couple days, actually. Wow. So, I want to try and figure out how to take the square root of a matrix. We have some matrix A, and then I take the square root. Can I do this? What does this equal? Okay. I actually don't know, so I'm going to try and figure it out in this video. So my first thought process is to go the exact opposite approach and see what it means to square a matrix. So if we still have the same matrix A, what does it mean to square this matrix? Well, squaring something is multiplying it by itself. Okay, so 1, 2, 3, 4 times 1, 2, 3, 4. Okay, what about, how do we do this? What is multiplication with matrices? Do I just say 1 squared, 2 squared, 3 squared, 4 squared? But what if we weren't doing A squared, we were doing A times B? Where B is 1, 3, 2, 4. How do we calculate this? Thankfully, I am in a linear algebra class right now. So I can do A times B. I know how to do that multiplication. But what does it mean? What does it mean to multiply A by B? My calculus brain, whenever I see two numbers being multiplied together, I think of area under the curve and integrals. Because if we have where A is 5 and B is 3, right? I think of a 5 by 3 rectangle. This is 5. This is 3. The area is 15. That's A times B. So can we do that with matrices? Let's slow down a little bit. We have a 2 by 1 matrix. And what it means is it's where a vector points. This vector is pointing from the origin to the point 1, 1. The matrix is 1, 1. So this vector we're going to represent as a linear combination of basis vectors. Basis vectors are these unit vectors in a given direction. So I hat is the basis vector in the x direction. So its x component is 1, its y component is 0. If you are liking this video so far, leave a like, subscribe. I want to do more of these math things, and this just shows that you appreciate them. 10 likes on this video and I'm going to do a completing the square geometric proof. And of course, don't forget to subscribe because I have an idea of how to experimentally measure the mass of the sun. That'll probably be up in a few weeks, hopefully. It's going to have really bad accuracy, I already know. I just want to see how far off we get. I'm expecting 10 million% error, but science. J hat is a basis vector. It's 1 in the y direction, but 0 in the x direction. Now we can represent this vector as a linear combination of these two basis vectors. So we could say this vector v is pointing 2 in the x direction, so 2 I hat, and it is pointing -1 in the y direction, so negative j hat. Okay, so then we can rewrite this as 2. Well, what is I hat? I hat is 1, 0, so 2 times 1, 0, minus j hat, which is 0, 1. Great. Now we can simplify this. So we're going to simplify this as, well, we can kind of figure out what this is going to look like, right? It's 2 in the x, pointing from 0, so it's going to be 2, and -1 in the y. -1. And then when we multiply this out, we say 2 times 1 minus 0 times 1 is 2. 2 times 0 minus 1 times 1, -1. So we can rewrite vectors in terms of I hat and j hat, and this kind of scalar multiplication is multiplying this term by each term in the matrix. Back in algebra class where we had x times something in parentheses, this means that this is distributed to each term. So now we have a new matrix, xy. It corresponds to some point arbitrarily as a matrix. So this is a distance of x away. This is a distance of y away. It corresponds to this vector. We want to move this vector, not literally move, but we want to multiply it by something so that it is transformed. This in linear algebra is what we call a transformation. We multiply this by some matrix, it gets rotated by some and scaled by something. So this is how we would write that. We have transformed it by this matrix. We'll call it matrix M. And the original matrix O. That's not confusing for 0 at all. So we transform this matrix O by using, here we'll call it transformation T. There we go, transformation T. I'll call this is going to be some matrix, and it still points in a direction. So we're going to define this as still a 1 by 2 matrix, and so we'll call this x2, y2, and I guess we can call this ka, Japanese ka. We use Greek a lot, why not use Japanese symbols? So this is now the Japanese, or not Japanese, this is now matrix ka. No, that was horrible. Ka. So, how do we calculate this? So if we wanted to figure out the multiplication of this matrix, of these matrices, how would we do that? We break it down. We're going to break this matrix and say, well, this is going to be scaled by this part of the matrix. So we're going to say 3 times this matrix, and then we add it with this part is going to be scaled by this part, scaled and rotated by this part. So now we can do this calculation because we can do scalar multiplication. We now say 3 times -3 plus -2 times 2. And that's the first term. Now we say 3 times 1 plus 2 times 2. And this works out to -9 minus 4 and then 3 plus 4 . So this works out to the 2 by 1 matrix, -13, 7. We had this original matrix, 3, 2, 3 over 2 up. We transformed it by this matrix, and we ended up over here at -13, 7. So in component form, we have a times x plus x times c and then c times y plus d times y. Okay, so now we can do that kind of multiplication. We're nearly back to our question. 2 by 2 matrix multiplication. This is the same thing as applying this matrix transformation, then applying this matrix transformation. So to figure out what the net rotation and scaling matrix is, we break it apart. And we now know how to do these. So the first term is going to be this times this plus this times this. Oh, times 2. This is exactly what we did before. Now we're going to say 3 times 1 plus 4 times 2. And this is our first column. The second column, this would be 4, is going to be now 1 times 3 plus 2 times 4. Now we're going to say 3 times 3 plus 4 times 4. We simplify all of this. 1 plus 4 is 5. 3 plus 8 is 11. 3 plus 8 is 11. 9 plus 16 is 25. So that's how we multiply two matrices. We're about at the extent of my linear algebra knowledge, but there's one last thing that I need to cover, and I've basically covered an entire semester's worth of linear algebra. This is probably going to be a 20-30 minute video, but it's fine. So if we write matrix A in terms of P, matrix P times D times the inverse of P, it's some set of matrix multiplication such that this is true. And we want to figure out matrices P, D, and P that do this. This is called diagonalization. And P inverse are inverses of each other. So what an inverse is, it's, for example, square and square root effectively undo each other. So this is x. E to the ln x, that's just x, basically. So in the matrix world, P times P inverse is I. That's a matrix such that when you multiply it by another matrix, it doesn't do anything. And you can check this multiplication. This will leave you with a 2 by 1 matrix, xy. So it's the effect of just 1, basically. But these are not right next to each other. So we're not just saying A is equal to D, but we can write it this way. So we want P to be in an inverse matrix, and D is going to be a diagonal matrix. So if we wanted, it would be something like this. So what we want to be able to do is when we say A to some power, we still have to do the multiplication at the end. But because this will end up effectively being 1 apart from some multiplication, we only have to square these. And then we can do the multiplication starting from right to left. So this is my theory on how we're going to compute the square root of A. Because the square root is the same thing as 1/2 power. I don't know if this is how it actually works, but it's my theory. So then, if we can figure out this, whatever these two values are and what these matrices are, then I think we can compute it. And then I'm going to then test my theory to see if it works by multiplying whatever we get from this by itself. And if we can get back the original matrix, then I'd say my idea works. And if not, you can roast me down in the comment section. It's just a theory. Okay, so we have this matrix B. We're going to try and rewrite it in terms of this. And then we're going to raise it to the 1/2 and see if it's the same as effectively a square root when we multiply whatever it is, we get this back. So what matrices, we're going to have A, B, C, D. Okay. Then for the diagonal matrix, we're going to have, what should I call these? F and G, 0, 0. And this P inverse is going to be the inverse of P. So to calculate the inverse, I can't even read. You flip these two entries, you invert these two, and then you divide by the determinant. So then the determinant is AD minus BC. So everybody gets divided by this. Cool. These are eigenvalues, and each of these are eigenvectors, and then we can figure this out later. So what is an eigenvector? We saw before that if we have a matrix, a 2x1 matrix, and then we transform it by a 2x2 transformation to go to something else, it will probably scale and rotate it. Okay. There might be some vectors, we don't know what it is, but there might be some vector, then we apply that transformation matrix, all it does is scale it. So if this had length 1, so new length is 2. It didn't rotate it at all. I didn't shear it, just scaled it. If a vector is only scaled by a transformation, then it is a eigenvector of that transformation. And its eigenvalue is how much it is scaled by. We have vector x, x1, x2 are its coordinates. We now say a times x. A times x, the eigenvector is the eigenvalue is now considered as lambda. Now these are all matrices. This is a transformation, but these are vectors, and this is a scalar. Well, if this is true, then we can do some algebra. Just subtracting lambda x from both sides. That's not supposed to be a weird eyeball. Okay, now we can factor out x. So now we have a minus lambda, and technically a is a kind of matrix, so this is okay. But we can't do a matrix minus a scalar. So I is kind of like 1 in the matrix world, just as I said before. And assuming that this is not the 0 vector, we now have to solve for this. And then to solve for this, to solve for these lambda values, we're going to take the determinant. I kind of showed what that was over here, of a minus lambda I. So let's figure that out for this matrix here. So first we need to figure out what b minus lambda I is. And then we can take the determinant. So b is obviously the matrix B. 2, 3, 1, 4. We don't know what lambda is, but we do know what I is. It's the identity 2 by 2 matrix. So lambda times 1 and lambda times 1. And then we subtract each term. So b minus lambda I is going to be 2 minus lambda, 3 minus 0, 1 minus 0, and then 4 minus lambda. So this is 1 and 4 minus lambda. Okay, great. So now we have b minus lambda I. So we want to take the determinant of b minus lambda I. Up here we did the inverse, but now we need the determinant. So the determinant is this term times this term, 2 minus lambda, 4 minus lambda, minus the product of these two. Okay, back to FOIL, Algebra 1. 2 times 4 is 8. 2 times negative lambda is negative 2 lambda. Negative lambda times 4 is negative 4 lambda. Sure. 4 lambda. And negative lambda times negative lambda is positive lambda squared. And then minus 3 for this term out here. Okay, let's simplify this. Lambda squared minus 6 lambda plus 5. So we could factor this, or we could complete the square. And this video is already long enough, so we're just going to factor this. I could show a really cool proof for the completing the square. 10 likes in this video and I might actually do that. So we need to figure out what multiplies to 5 and adds to negative 6. It's going to be lambda minus 1 and lambda minus 5. Great. So this means that lambda, the zero product property, says now lambda equals 1, lambda equals 5. With lambda equals 1 and 5, we know that these are our diagonal values. Now we need to figure out the corresponding eigenvectors. There's going to be a vector AC when applied this matrix transformation. We'll get the vector AC times 5. And the same thing, there's going to be a vector BD when applied this transformation is going to get this vector BD times 1. Okay, for lambda equals 5, we're solving for V1. So now we say B times V1 is 5 times V1. We know. That's what an eigenvector is. So now for V1, we're going to solve this. And this, because this is a 2x2 matrix, this is like solving a systems of equations. So then we're going to do B minus, let's write out the systems of equations first. So 2 minus 5 times x1 plus 3, and then for the identity matrix we don't subtract anything. 3 times x2 is equal to 0. And then for this term, it's just going to be 1. x1 plus 4 minus 5 x2 is equal to 0. Now we can solve the systems of equations. So then I put the entries of these in an augmented matrix. 2 minus 5 is negative 3, 3, 1, and then 4 minus 5 is negative 1. Then I set what is equal to on the right. Now I'm going to perform a series of row operations to try and figure out these values. And then if there's a free variable, we'll choose easy variables. I realize that this is just 1/3 of the first row. So if I say 3, 1/3 R1 plus row 2 replaces row 2, then we're going to get this matrix, which corresponds to 0x1 plus 0x2 equals 0. That doesn't help us. But negative 3x1 plus 3x2 equals 0. Dividing everybody by 3 and moving things around we get x1 equals x2. Okay, x2 is a free variable, so we can choose anything, and let's not choose the 0 vector. And let's work smarter, not harder. The non-zero eigenvector for lambda equals 5, V1 is 1, 1. Alright, let's figure out V2. Same process. We get this matrix, and then solving, we get x1 plus 3x3 equals 0. So then we can choose. We need to choose something such that x1 is equal to negative 3x3. Well, let's make this easy. I'm going to let x3 equal negative 1. x3, this is supposed to be x2. We're going to let x2 equal negative 1. So when I write this is negative 1. Negative 1 times negative 3 is going to be 3. So now I have my vectors. Okay, so our P matrix is our matrix of eigenvectors. 1, 1, 3, negative 1. Okay, our matrix D is the table of eigenvectors. 5 corresponds to the first one, and 1 corresponds to the second one. Okay, so we have our matrix D now. Now I need our P inverse matrix. So first we need to take the determinant of this. Negative 1 times 1 is going to be negative 1, minus this times this, which is going to be 3. All of this is going to be just 1/4. And then this, we're going to switch these terms and negate these. So all of this to say, this is our P inverse matrix. So now this is our matrix B. So if I said B to the K, because this is one we don't even have to do, K. Okay, so now we do multiplication, 5 to the K times 1/4, plus 0 times 1/4. For this entry, 0 times 1/4 plus 1 times 1/4 is just 1/4. For this entry, we do this times this, plus this times this. So 5 times K times 5 to the K times 3/4 plus 0. Okay. Now this times this, 0. This times this, negative 1/4. Alright. Now this times this, 5 to the K times 1/4, plus this times this, the row dotted with the column this times this, plus this times this. So plus 3/4. That's the first entry. So now it's the row dotted with the column. So this row, we're going to dot with this column. So 5K times 1/4, or 5 to the K times 1/4, minus 1/4. Okay, the row dotted with the column, 1 times that, so 5 to the K times 3/4 plus that, and then the row dotted with the column, 5K times 3/4 minus this times this, so it's going to be plus 1/4. So now we have an equation, or I guess a matrix, for B to the K. We now have an equation for B to the K. So finally, we know that square root B is going to be B to the 1/2. So now we're going to test this. We're going to substitute in these values where K equals 1/2. So doing all of that, we get this. This is the square root of that. It is definitely not just taking the square root of each term. If this really works, squaring this should give us this. So we square the 1 individually, and then we square this matrix. We're going to test it to see if my theory checks out. Well, once you've done so much foiling you could pass an Algebra 1 class, we get this, divided by 16. 32 divided by 16 is 2. 48 divided by 16 is 3. 16 over 16 is 1. 64 over 16 is 4. Well, wouldn't you know, that's the original matrix. So we can use diagonalization to figure out the square root of a matrix.